In the final section of Chapter 6, we're going to use trigonometry to study a concept that we're already quite familiar with, and that is complex numbers. We're going to go over some ways to perform operations with complex numbers using trigonometry, and sometimes the use of trigonometry will make the operations with complex numbers a lot easier to deal with. Section 6, titled De Moivre's theorem and nth roots. De Moivre's theorem is such a theorem that actually does powers of complex numbers, but it does it in a trig form. That's kind of the end objective in this section where we're going, and that's kind of the last thing we'll get to. Well, first, what is a complex number? We should be quite familiar with complex numbers. In standard form, a complex number is one of the form a plus bi. Our text uses the letter z to name complex numbers. A complex number is one that has a real number and an imaginary number, or a real part and an imaginary part. Has to have both, the real and imaginary part, to make a complex number. Example would be 4 plus 3i, complex number. Now, complex numbers can be graphed. They can be graphed in what looks like a rectangular coordinate plane, graphed in a complex plane. But it is just the rectangular plane you're used to dealing with, except we label the axes the real axis and the imaginary axis as opposed to the x and the y axis. And then we can plot a point based on the real part being the horizontal component and the imaginary part being the vertical component. So any point, any complex number a plus bi can be plotted on a complex plane. Now we also like to talk a little bit about absolute value. Absolute value, we know, is the distance that a value is from 0 on a number line, and for a complex number it's the distance the number is from the origin on the complex plane. So the absolute value is that right there. This is the absolute value, a plus bi. To find the absolute value, it's simply a Pythagorean's theorem computation. If we were to come straight down and straight across, making a right triangle that is a and b on the legs, that's the computation you see right here, the square root of a squared plus b squared, directly from Pythagorean's theorem, right triangle construction. First example says graph and find the absolute value. So graph this complex number. We'll just sketch our own rough graph. Okay, so this complex number, negative 2 plus 5i, is going to go negative 2 on the real axis, 5 on the imaginary axis, and it plots right there. Now I want to find the absolute value of this complex number. So again, it's a right triangle construction. You can do it by going straight down to the real axis, straight across, and the absolute value then is the hypotenuse of that triangle. This measures length 2 and 5, so the Pythagorean's theorem, or the absolute value of our complex number, is the square root of 2 squared plus 5 squared. Notice I dropped the negative because I'm considering it as just the length on the side, but even if you just used the negative 2 as like 2 to the left, it'd still be just the same, because if I were to put that negative and square the negative, it's still going to be positive. So it really does not matter there. It's 4 plus 25. The absolute value is the square root of 29. So you might have asked so far, where does the trigonometry come into play with complex numbers? Well, if we can plot a complex number and we can construct a right triangle out of that complex number, then it offers us an opportunity for some right triangle trigonometry. This absolute value distance right here, if I connect a line segment there, make the hypotenuse of this triangle, well, it forms an angle theta with the real axis, or with the, you can think of it as the positive x-axis. Very, very similar to how we rewrote vectors in a trigonometric form, we can write a complex number in a trigonometric form. You know, it kind of works like this. I'll maybe redraw it here so the drawing on the left doesn't get too confusing. So if we plot this complex number a plus bi, and we build a triangle out of this. Well, the links on the legs, of course, are a to the right and b going up. And if we use some trigonometry, and we'll call this, let's throw a value here actually first. Let's call this r, just for the length of the hypotenuse. Well, we could say that the sine of the angle theta is equal to the opposite over the hypotenuse, or that the value b is equal to r times sine theta, and that we see right here. But this is how we got to it, of course. We could also say that the cosine of theta is equal to the adjacent over the hypotenuse, or that a equals r times cosine theta. We see that right there. Okay. Well, so that then leads us to some substitution that we can write the trig form of a complex number. If a complex number z equals a plus bi, and a is this and b is this, then the complex number becomes r times cosine theta plus r times sine theta times I. And it's often written then with the r factored out, r times cosine theta plus the imaginary unit I, I'm just going to pull to the front, I sine theta. That is generally regarded as a trig form of a complex number. Well, if we're going to be working with complex numbers in this trig form to perform operations with them, we need to know how do we put a complex number in trigonometric form. So we'll start there. So here we have a trig number, could be considered, or a complex number, sorry, could be considered z equals square root of 3 plus I. And if we're of the form a plus bi, then that means that the a is square root of 3 and the b is 1, as it's 1i. Now let's find, well, what do we need? Let's find what we need first. We need two things. We need to find the r and the theta. The r is the, essentially the r is the absolute value. It's the length that the point is from the origin. So we can find the r by doing the square root of square root of 3 squared plus 1 squared. That is the square root of 3 plus 1, which is 2. The theta we'll find the exact same way that we find direction angles of vectors. We'll take tan inverse of, it's going to be an opposite over adjacent, which go back and look at your triangle from the last slide. That is tan inverse of the y value, or the b, divided by the a. Now that's the same as tan inverse square root of 3 over 3. And so we need to figure out where on our circle does that happen. Might even actually be easier to do it right here. Let's change colors here. This would represent the ordered pair point square root of 3 over 2 comma 1/2. Since tangent is the y value divided by the x value, the halves of course canceling. And so at what angle do we find that point? And that point lives at pi over 6. Okay, so we have now the r, we have the theta, we can write the trig form of this complex number it's going to be r times cosine of theta plus I sine of theta. And that would be done. The last slide showed us how to get to trig form of a complex number if we were given standard form. This one's actually asking us to do the exact opposite of that. Here we have trig form of a complex number. We want standard form. It's actually much easier to do. We're just going to distribute this r value. So we have square root of 2 cosine 7 pi over 6 plus I square root of 2 sine 7 pi over 6. The cosine 7 pi over 6 and the sine of 7 pi over 6. You need to use your circle to look up those numerical values, those exact values. So we'd have the square root of 2 times the cosine of 7 pi over 6 is negative square root of 3 over 2 plus I square root of 2. The sine of 7 pi over 6 is negative 1/2. And so if we multiply this together, we get negative square root of 6 over 2. The plus I'm going to change to minus, minus, and I'll have square root of 2 over 2I. And there's our complex number in standard form. Alright, the next slide offers a couple of problems that we've seen as far back as Algebra 2 and college algebra / pre-calculus type course. How do we perform operations with complex numbers when they're in standard form? So here we see a product of two complex numbers. This is simply a FOIL type problem. If we FOIL this, we get 10 plus 5i minus 6i minus 3i squared. That is 10 minus I minus 3i squared. Now you might recall, hopefully recall, from our algebra days that I squared is the same as a negative 1. So this number is really a positive 3. Added to the 10 makes 13 minus I. When we divide complex numbers, if there are multiple terms in the denominator, if there's a binomial in the denominator, as there is in this problem, we multiply top and bottom by 4 minus I, conjugate pair of the denominator. Now we do have to FOIL the top. So if we FOIL that, we get 12 minus 3i minus 8i plus 2i squared. When we FOIL the denominator, of course, since we've got opposite signed pairs, all we have to do is the first and the last, as the outside inside, are going to cancel out. So that's 16 minus I squared. The numerator, let's just go a little faster here. This positive 2i squared is really the same as a negative 2. So that makes 10 minus 11i. And this negative I squared is really the same as a positive 1. So over 17. If we split it up, we get the fraction 10 17ths minus 11 17ths I.